Have you ever noticed exactly what your hands naturally do when you pick up a messy hand of playing cards? Without even thinking about it, you naturally split the cards into two distinct groups. You build a neat, organized pile on one side of your hand, while the messy, unorganized cards stay on the other. To clean up the mess, you pluck a single card from the unorganized side, slide the sorted cards over to make a little room, and drop the new card right into its perfect numerical spot. If you've ever done this, you already understand the mechanics behind a classic computer science process. It's called insertion sort. Let's see how a computer mimics this using numbers 8, 3, 5, 1, and 6. We draw a line separating sorted from unsorted. The first number on the far left becomes our already sorted pile. The goal is to grow that section until completely empty. The computer picks up the first unsorted number, the 3, and compares it directly to the 8 to see where it belongs. Because 3 is smaller, the 8 slides one space to the right to create an empty gap. With that space now open, the 3 drops right in, and our first pass is finished. Next, the computer grabs the 5. It looks at the sorted pile and checks the numbers from right to left, searching for the right spot. It sees that 5 is smaller than 8, so the 8 slides over. But when it checks the 3, it sees the 5 is larger, so it stops searching and drops the 5 into the gap. The computer isn't just shuffling things around, it's systematically moving larger numbers out of the way to make sure the left side stays in order. Now, look what happens when we hit a very small number like the 1. The computer checks it against the 8, the 5, and the 3. Since 1 is smaller than all of them, it triggers a domino effect. Every single number in the sorted section has to slide one position to the right to make room. With the whole pile shifted over, the 1 can finally drop into the very first spot at the front of the list. Finally, it reaches the 6. It checks the 8, moves the 8 over, but stops when it hits the 5. The 6 drops into place, and the work is done. There are no more numbers left on the unsorted side, which means our list is now fully organized. By repeating this sliding and inserting pattern, the computer builds perfect order without skipping a single step. To decide if this is the right tool for a job, we look at its time complexity. This is just a measure of how the speed changes depending on how messy the data is. If a list is already perfectly in order, the computer just checks each item once and finishes almost instantly because it never has to slide anything. But if a list is completely backwards, it's a different story. The computer has to shift every single number on every single pass, which makes it very slow for large amounts of data. We also look at space complexity, or how much extra digital memory the computer needs to get the job done. Some methods need to create entire duplicate lists to finish the sort, which eats up storage. Insertion sort does all its work within the original list. Whether you are sorting 5 items or 5,000, the amount of extra room the computer needs stays exactly the same. This makes it an incredibly memory-efficient tool. You wouldn't use this for a massive database with millions of rows, but for small lists or lists that are already mostly in order, it is often the fastest tool available. It's also very reliable when you have items that are identical. If you had 2 different cards with the same number, insertion sort ensures they stay in their original order, never accidentally swapping them. Because it's so predictable and uses so little memory, engineers use it as a building block. They often use it to handle the final steps of much more advanced sorting systems. By understanding the simple logic of sorting a hand of cards, you've learned a pattern that helps computers organize information efficiently. You're now seeing the world a little more like a programmer does.